Hello everyone, and welcome to Module 8, Repeated Outcome Measures in SMARTS. My name is Easton Huch. I'm a third-year PhD student in the D3 Center, and I'm excited to be presenting this module to you. So in previous modules, we've already learned about how to analyze a SMART that has a single outcome measured at the end of the study. That's what we already know how to do. What's new in this module is that now we're considering the setting where we collect related outcome measures at multiple time points. So not just the beginning of the study, but perhaps the beginning, middle, and the end. One example might be collecting students' academic performance throughout the course of the school year. The structure of the module will look like this. We'll have 4 sections. In the first section, I'll give an overview of SMART designs that have repeated outcome measures. Then we'll talk about the scientific questions that you can answer with this type of SMART. Then we'll go over the data analysis methods that you can use. They're similar to what you learned in the in-person days, but there are some special things you have to account for. And then lastly, we'll briefly talk about sample size considerations for planning SMARTs of this variety. So now we'll dive into the designs themselves. So let's look at the ADHD SMART that by now you are all familiar with and love. So the first stage here randomizes participants to either medication or BMOD, which is behavioral modification therapy. Then from there, we assess response status at week 8. Responders continue with their first stage treatment. Non-responders are randomized to either augment or intensify their first stage treatment. So you've already seen this diagram before. What's new is if you look at this bottom axis here, previously we just had one end of study outcome, just a single Y. Now, however, we have Y1, Y2, Y3, and Y4. So that's what's new here. As a reminder, within this study, there are really 4 embedded adaptive interventions. There are 2 that start with medication, 2 that start with BMOD, and then within each of those pairs, one will assign the participant to augment if they are a non-responder, the other will assign to intensify if they're a non-responder. And otherwise, all of them continue. So those are the 4 embedded adaptive interventions. If you remember the typical primary aims that we talked about during the in-person days, the typical primary aim 3 was to compare embedded adaptive interventions in terms of a single end of study outcome. So in this case, it would be either Y3 or Y4. So we can still do that if we have repeated outcome measures. However, now we have this additional information, right? We don't just have Y4 or just Y3. We have Y1, Y2, Y3, and Y4. So that allows us to think a little bit more creatively about ways of measuring the impact of these adaptive interventions. So take a minute to just think about, are there other ways in which you might want to compare these adaptive interventions given that you have multiple outcome measures? All right, hopefully you at least had an idea or two about different things you might look into. Now we're going to talk about some of the scientific questions that you can answer with repeated outcome measures. And perhaps one of the ideas that you had will be related to one of the questions that we talk about here. All right, so really there are, I would say, 3 variations of AIM type 3 when you have repeated outcome measures. You can still look at end of study outcomes. We'll talk about why you might still want to do that and the special things that you can do with repeated outcome measures. You can also look at what we'll call time averaged outcomes. The most common metric here is the area under the curve. You can get a sense of not just what is this measurement, the average value of this measurement at a particular point in time, but instead on average throughout the course of the entire study, what is the typical or average value of that variable. And then lastly, you could also consider outcome trajectories. So not just a single point in time, not like the total or time average, but instead, what does the trajectory itself look like? and this is sometimes called delayed effects. For time, we won't be able to talk about outcome trajectories in much detail, but we'll refer you to Shi et al. 2015 if you want to learn more. We'll talk about those first two scientific questions though. We'll start with end of study outcomes. So in this case, the scientific questions look like this. Is AI1 better than AI2 in terms of academic performance at the end of the school year? So that's the question. And freezing it as an aim, it might look like this. We want to compare AI1 and AI2 in terms of academic performance at the end of the school year. So at this point, you might reasonably be wondering, why would I even collect repeated outcome measures if I just care about a single time point? And really there's two reasons for that, which are listed here. One is that you actually get some statistical efficiency gains by including these additional repeated outcome measures. And the reason for that is you can effectively denoise the outcome variable. If I know someone's test score at the beginning of the study, that gives me some information about what their test score is likely to be at the end as well. So there are ways of leveraging that such that you get increased precision or power. The other reason you might collect repeated outcome measures is that you might have secondary or exploratory aims that do involve other time points. So you might have chosen, kind of a standard single time point primary aim. However, nothing stops you from specifying a secondary aim or an exploratory aim that does look at something else. Perhaps your secondary aim is to look at a time averaged outcome, for instance. Now we'll spend a few minutes talking about time averaged outcomes. So in this case, the scientific question would be, is AI1 better than AI2 in terms of typical academic performance? And by typical, what we really mean is averaged across time. The primary aim is going to look like this. We want to compare AI1 and AI2 in terms of area under the curve, AUC, for academic performance. So this primary aim is going to be especially relevant if we want to optimize the typical value of an outcome over time as opposed to a single value at a specific point in time. Thinking back on the ADHD study in particular, AUC seems like a very natural choice because there the goal is not just for students to perform well at the end of the school year. Instead, it's for them to be performing well throughout the entire school year. The next few slides depict area under the curve, AUC. So the data we're going to be showing is just hypothetical. Let's say we run the study and then the expected school performance follows this trend that we're showing in this graph here. Now this is for adaptive intervention 1. In this case, the AUC would be the area of this red region. And you can think about it as being the average performance for this group of students over the course of the entire school year. Let's say that we run the study and the results for AI2 look like this. It starts in about the same spot, it ends in about the same spot, but in the middle the performance is substantially higher. So now the difference in AUC is going to be this blue region in between the two lines. If we were to compare these two adaptive interventions in terms of just the end of school year outcome, what would we conclude? Well, we probably would fail to find a difference at all, and if we did find a difference, it would likely be very small. In contrast, if we were to use AUC, which is probably the better measure here of the effect of these adaptive interventions, then not only would we be more likely to find an effect, but we'd also be more likely to find a significantly larger effect. All right, that is it for the scientific questions. Again, if you're interested in the third type of scientific question, we'd recommend looking at the paper that we've linked. Now we'll go ahead and move on to the data analysis methods that we use for repeated outcome measures. So we're going to start with a review of the analysis that you've already learned for end of study outcomes. There are going to be 3 steps. The first step is to weight and replicate the data. The reason this comes into play is because of the randomization scheme, right? We have responders and non-responders. In this study, the responders are only randomized once to the first stage intervention. They don't get randomized again. However, the non-responders do. So the weighting accounts for over and underrepresentation because of that randomization scheme. The replicating appears because there are participants that are consistent with more than one adaptive intervention. So there are students who are responders, and they're consistent with an adaptive intervention where they would have been randomized, I guess would have been assigned, we'll say it that way, to augment their treatment, or would have been assigned to intensify. So they essentially need to be included in both of those adaptive interventions for the purposes of performing the analysis. The other reason we do this is just that it makes the analysis more convenient. We can use standard statistical software to do simultaneous estimation and comparison of adaptive interventions. Step 2 is to select and fit a model. And this is the type of model that we've already seen for standard smarts. We have an intercept, beta 0. We have main effects, beta 1 and beta 2, for the first and second stage interventions, respectively. And then lastly, we have the interaction term, which tells us if the effect of one intervention depends on the level of the other. And then from there, we estimate linear combinations of parameters in order to compare the two adaptive interventions, AI1 and AI2. So the way we do this is pretty straightforward. So looking at AI1 first, under AI1, the students were assigned to receive medication. So we plug in -1 for A1. And then in the second stage, they were assigned to -1 again, which is augment. So we can just plug those values in, and then we do the same for AI2, the only difference being the first stage intervention is different. So for that one, we plug in AI1 equals +1. So plugging those in, we get these two expressions down here, each one corresponding to the mean of the outcome under that adaptive intervention. So if we want to compare two adaptive interventions, what do? We look at the difference between these, right? So we're going to look at AI1 minus AI2. And if you work through the algebra, you get this expression on the right, -2 beta 1 plus 2 beta 3. So that's going to correspond with the average difference in the outcome between these two adaptive interventions. All right, so that's the end of the review for smarts with a single end of study outcome. Hopefully most of that was familiar to you. Now we're going to think about this module in which we have multiple outcome variables. We have repeated measures. And we're going to think about how we can adapt this strategy that we've already learned to the setting where we got this Y1, Y2, Y3, Y4. Turns out the general steps are going to be the same. We're still going to have 3 steps. First, we're going to weight and replicate the data. The complication, however, is that now we have multiple rows per individual. So let's say I was in the study, then you're going to have a row in your data set for 10.0, and then week 8, end of semester, and end of year, right? So the solution turns out it's pretty straightforward. All we have to do is replicate each of those rows for the responders. So let's take a look at some fake data. So in this case, looking at the first 4 rows, this individual was a non-responder. So that means we don't have to replicate that data at all. That individual is consistent with only a single adaptive intervention. Looking at this second participant, however, we see that their response status was 1, meaning they were a responder. So they were actually compatible with 2 embedded adaptive interventions. one with AI2 equals to 1 and another with AI2 equal to minus 1. So we just take each of the original rows, create a copy, and then in one we put a positive 1, and then in the other we put a minus 1. Notice also that we've changed the weights. So here we're assuming that the randomization probability is 0.5. So in that case, you get a weight of 4 for this first participant and a weight of 2 for the second. So that's the first step. It's largely the same as what you've already seen, just you have multiple rows. Now we're going to talk about the model. The model does get a little bit more challenging. Previously, we fit a model that had this structure here. We've got the intercept, main effects, and an interaction. We could do something similar with repeated outcome measures. We just have to be a little bit more thoughtful. And the reason for that is now we have a temporal ordering to all of these variables, right? We observe these variables first, then these, and then finally we've got our end of study outcomes. So we need to set up the model such that each outcome can only be affected by interventions that have already occurred. So we'll walk through some examples here. So let's think about Y4 first. So Y4 can be impacted by both A2 and A1. And the reason for that is that both of those interventions occur prior to Y4. The same is true of Y3. The ordering is such that the treatments or interventions occur prior, so you in general would expect there to be some effect on Y3. The story gets a little more interesting for Y2 though, because Y2 occurs after A1 but before A2. So we need to set up our model such that A1 can affect Y2 but A2 cannot affect Y2. And then of course for Y1 occurs before either of the treatment options, the interventions. So for that reason, AI1 and AI2 should not be able to affect the expected value of Y1. It should be the same regardless of what treatment options the participants were assigned to afterward. Now the reason we're spending so much time on this is that if we don't properly account for the ordering of the measurement occasions relative to the intervention options, that can actually introduce bias into our analysis. So in a moment, we'll talk about how to set up the model mathematically such that we obey these temporal ordering constraints. First, let's talk a little bit more conceptually about what we're trying to do, and then hopefully the math will be a little more straightforward. So conceptually, we want it to be the case that the expected value of the school performance is the same across all 4 adaptive interventions. That's why when you look at this figure, initially all of the adaptive interventions start at the same point. The y-intercept is the same. Once the school starts, however, we're going to allow these lines to diverge. And the reason for that is that 2 of these adaptive interventions start with behavioral modification and the other 2 start with medication. So in general, we'd expect to see differences in the outcomes based on that first stage intervention option. Starting at week 8, we would expect the individual adaptive interventions to diverge again, and that's because at that point, the second stage intervention has been assigned. The participant either is assigned to augment or intensify their treatment, or if they're a responder, they just continue, right? So at that point, we need to allow AI1 and AI3 to have different expected values, and similarly, we needed to allow AI2 and AI4 to have different expected values. And then no additional treatments occur, so from week 8 onward, each adaptive intervention just has its own line that isn't any longer connected to another adaptive intervention. Okay, so conceptually, that was the idea. Now we're going to start walking through how you set up the math such that your model actually obeys these constraints. To do that, we're going to introduce two helper variables, S1 and S2, that will make it easier to set up our model. So conceptually, each of these variables is going to represent the amount of time that has elapsed within a given stage. And in particular, we've coded it below such that the number corresponds to the number of months that have elapsed. So let's look at this first time point. So initially at the start of the school year, both of these variables, S1 and S2, are going to be equal to 0. And that's because no time has elapsed in either of the stages. Then 2 months in, we're going to set S1 equal to 2. And the reason for that is that 2 months have elapsed within stage 1. No time has elapsed in stage 2, however, which is why S2 is still equal to 0. Then at time t equals 4, we set S1 to 2. It doesn't increment anymore because stage 2 stops after 2 months. So no more time elapses in stage 1. And then we'll set S2 equal to 2, because at this point, 2 months have elapsed in stage 2, right? We got the time from month 2 to month 4. Then lastly, we'll look at time t equals 8. So at this point, still 2 months have elapsed in stage 1, but 6 months have elapsed in stage 2. So that's why the second variable S2 is now equal to 6. There's 4 months in between these last 2 points here. All right, so we're going to use these two variables in order to modify this model that we already have. So for now, let's think about everyone being on a single adaptive intervention, and then we'll talk about how to generalize to multiple adaptive interventions. So we're going to try and fit a model that looks like the one we fit previously. So we're going to have beta 0, which corresponds to the expected school performance at the beginning of the school year. This is an intercept term. Then we're going to have another term, beta 1, which is a stage 1 slope. This is the expected monthly change in school performance during stage 1. And then lastly, we've got beta 2, which is the stage 2 slope. This is the expected monthly change in school performance during stage 2. So thinking back to our diagram earlier, right, where we had the lines and then they started to diverge and then they diverged again. Beta 0 is going to represent that initial y-intercept. Beta 1 is going to be the slope during stage 1, and then beta 2 is the slope thereafter, right? So that's what these values correspond to. That's at an intuitive level. The difficulty now is we actually have to think about how these slopes change based on the interventions that people receive. We'll start with beta 0. This one is the easiest, and the reason for that is that no treatments have occurred. So beta 0 does not need to be affected at all by A1 or A2, and in fact it shouldn't be affected by them. With beta 1, however, we do have to start thinking about the impact of the treatments, right? In general, we're going to expect that A1 will affect beta 1. And the reason for that is that you're likely to have a different slope depending on if you start with BMOD versus medication. So what we'll do is we'll replace beta 1 with beta 1 0 plus beta 1 1 times A1. So just thinking about this a little bit, beta 1 0, that's going to be the slope kind of on average. It's kind of like a main effect. And then beta 1 1 is essentially telling us how that slope changes based on A1. All right, now let's think about beta 2. So for beta 2, at this point, A2 has already occurred. So every adaptive intervention is kind of on its own now. The expected school performance is likely to be different within each one. So for that reason, we need to allow the the slope here, beta 2, to depend on both A1 and A2. So we'll replace beta 2 by these 4 terms. And you can see now this has the same structure as the models we've seen previously, right? We have something like an intercept, we have main effects for A1 and A2, and then lastly we have this interaction. So setting it up like this is going to allow beta 2 to be different for each of the 4 adaptive interventions. If you think back to our figure earlier with all the different lines, this expression here is going to give you each of the 4 slopes that you saw in the final section of the figure. All right, so putting it all together, our final model then takes this structure here. So we have beta 0, our intercept, that doesn't change. And then we have this second portion where we multiply everything by S1. And for that one, we just have beta 1, 0, something like an intercept within that group, plus beta 1, 1 times A1. So we're allowing the first stage intervention to affect the slope. And then similarly for the second one, we've got S2 multiplying this expression here with 4 values. This is allowing the second stage slope to depend on the second stage intervention option and the first stage intervention option as well. Okay, you made it to step 2. Now let's talk about step 3. So for step 3, we need to estimate linear combinations of parameters to compare AI1 and AI2. So the good news is that the estimands are still linear combinations of parameters, so you don't need to learn any new complicated statistics to do this step. We're going to follow the same strategy as last time, which is that for each adaptive intervention, we're just going to plug in the appropriate value of A1 and A2. So under AI1, we're going to plug in A1 equals -1 for med, and A2 equals -1 for augment. And you also need to think about the time point at which you're trying to estimate the expected value. So below, what we're estimating is the expected value of Y4. So that's why here we're plugging in 2 and then 6 for S1 and S2. Those are the values of S1 and S2 at the end of the study, which is when we collect Y4. So working through all the math, we get this expression on the bottom here. And then we can do the same thing for AI2. The only difference is that now we plug in A1 equals 1 because these participants receive B mod instead of med. And then lastly, we calculate the difference and we get the expression highlighted in yellow at the bottom, -4 beta 1, 1, -12 beta 2, 1, plus 12 beta 2, 3. So maybe it looks a little bit more complicated than previously, but it's still a linear combination of parameters, which is very easy to handle with these statistical tools that we've already used. And with that, you have made it to the end of the analysis section. So the last thing we'll do is spend a few minutes talking about sample size considerations for planning smarts with repeated outcome measures. So the sample size formula in this case takes on this form here. So capital N is the number of participants that we need for the study. And then we'll briefly review some of the things here that you've seen before, but maybe are not fresh on your minds. So alpha 1 is the type 1 error rate. And you want that to be as low as possible given the constraints of your study. And then we've got 1 minus beta over here, which corresponds to the power. So you want the power to be high because the power is the probability of detecting an effect given that 1 is present. So if you make the type 1 error low and if you make the power higher, that's going to make it so that n needs to be larger. All right, then there's delta, which you've also seen before. Delta is the standardized effect size for the comparison. That says how large of an effect do you think or do you hope you might be able to find in your study. So if you expect to find a very large effect, then actually you don't need that big of a sample size. On the other hand, if you think the effect is very small, then that means you're going to need more participants. I'm going to skip to R. You've seen R before, but R is the probability of response to first stage treatment. So this one I think is useful to think of in terms of the extremes. So first, let's think about the extreme where everyone is a responder. So in that case, R is equal to 1. So looking at the formula here, we would get 2 minus 1. This piece would just become 1, right? So in that case, we don't need as many participants. And the reason for that is that we essentially only have 2 interventions, right? And they're not really even adaptive at that point because we just assigned them up front, right? You just have a standard 2-arm trial. Now thinking about the other extreme, let's say that R is 0. That means everyone's a non-responder. In that case, the sample size will be twice as large because we'll get 2 minus 0 here. And the reason for that is that in that extreme, we really have 4 options, right? We have each of the 4 adaptive interventions. So we're going to need a larger sample size in order to be able to make all of the comparisons we want with sufficiently high power. Okay, now we'll talk about the new part here, which is this term 1 minus rho squared. So rho is the within-person correlation. Specifically, it's the within-person correlation under a compound symmetric correlation structure. So let's just kind of think through the extremes again here. So let's say that rho is 0. Then this term just works out to being 1. On the other hand, let's say that rho is very large. I guess it could be, 0.9 or like minus 0.9. The sign doesn't matter, but the magnitude does. So let's say it's very large, it's like 0.9. Then we get 1 minus 0.9 squared, which is roughly 0.2. So in that case, we don't need as many participants. And then conceptually, what's the reason for that? The reason is that there are some statistical benefits that you can reap because your outcomes are correlated. In effect, you're using the outcomes that you've collected earlier in the study to kind of denoise the outcome that you're measuring and whose expectation you're estimating at the end of the study. Then this table just kind of works out what those sample sizes look like for different values of delta and rho. So first we'll look at the case where rho is 0. So in that case you can see when we expect a small effect size, we need a relatively large number of participants, right? 559 versus 201 is a pretty sizable difference. And that trend continues throughout, right? For any value of rho, it's always the case that you don't need as many participants if you expect a large effect. Now let's look at the effect of the correlation. So if you compare across now, we can see that the number of participants is highest when rho is small. So rho equals 0 is the worst case, right? That would mean that the repeated outcome measures are just completely unrelated to each other statistically. They're uncorrelated. So in that case, you don't really get any benefit from the additional measures that you've collected during your study. But you can see as you move on to the right here, the number of participants decreases, and that's because the repeated outcome measures become more correlated as rho increases. So when rho equals 0.6, you're actually getting a sizable benefit from including these repeated outcome measures. Instead of recruiting 559 participants, which is a lot, you need to recruit only 358. It's also worth noting that you have to plug in values of these other parameters in the formula. So in order to create this table here, we plugged in 40% for R, we used 0.05 for alpha, and 80% for the target power. And the way you use these two values is you just calculate the z-score that's in the formula on the previous slide. All right, and the last thing we'll point you toward is we do have some R code that implements the methodology covered in these slides. It comes from John Ziek, who is a member of D3C, so you can look at his code here, which is available on our website. And then lastly, if you're interested in learning more about these methods, here are some references that we encourage you to go through. In particular, if you want to learn about the aim type we didn't have time for, you can take a look at some of these references. Thanks for listening. I hope you enjoyed it, and I hope it ends up being useful to you in your own research.